Have you ever stared at a spreadsheet just packed with numbers and thought, what am I even looking at? It's just noise, right? A total mess. Well, today, we're going to put together a kind of data storytelling toolkit. We're going to learn how to go from that data chaos to some crystal clarity using a few of the most powerful and fundamental tools in statistics. Okay, let's jump in. So picture a giant company, someone like Colgate-Palmolive. I mean, these guys operate in over 200 countries. They have a ton of products, everything from toothpaste and pet food to soap. Every single day, they are just flooded with information. Sales numbers, customer reviews, supply chain data, you name it. It's an absolute avalanche of data. So here's the million-dollar question. They've got these mountains of data, but raw data by itself, it's pretty much useless. How do they actually turn all that noise into real answers? Answers to questions like, hey, what's our best-selling product in Brazil? Or is that new ad campaign actually working? Well, the answer to that is the starting point for all data analysis. It's called descriptive statistics. All right, let's open up that toolkit. Our very first tool is for handling this simple stuff. Data that's not really numbers, but, categories or names. Things like brand names or different types of products. Now, if you want to get technical, the stats folks call this qualitative data. And our first job is just to get it all sorted out. Take a look at this. It's a simple list of 50 soft drinks that were bought at a store. Right now, it's just a wall of words. Can you tell me, just by glancing at this, which drink is the most popular? It's kind of hard, isn't it? Your brain has to scan the whole list, keep a running tally. It's slow, and you could easily make a mistake. This, right here, is data chaos. So, the first tool we're going to use to fight this chaos is called a frequency distribution. Now, that sounds super technical and complicated, but I promise it's incredibly simple. It's really just a fancy name for a table that counts how many of each thing you have. That's it. We're just making a list and counting them up. And boom, here is our frequency distribution. All of a sudden, the story just jumps right off the page, doesn't it? You can see immediately that Coke Classic is the hands-down winner with 19 sales. Pepsi is in second place, but it's not even close. And just like that, the chaos is gone. Now we have clarity. Okay, a table is great. It gets the job done. But let's be honest, our brains are just wired for visuals. We can make the story even clearer, even more powerful by turning it into a picture. And here you go. This is exactly what I'm talking about. On the left, you've got a bar graph. The taller the bar, the more people bought it. Simple. On the right, a pie chart. The bigger the slice, the bigger its share of the sales. For either of these, you don't even need to read the numbers to see that Coke Classic is king. That right there is the power of visualization. Okay, so sorting a few categories, that's one thing. But what happens when our data isn't just a handful of brand names? What if we're dealing with a total flood of different numbers? Well, that's going to require a slightly different but just as powerful tool from our kit. So let's check out a new problem. We've got data from an accounting firm, and it shows how many days it took them to complete 20 different year-end audits. The numbers range all the way from 12 days up to 33 days. And just like with the sodas, right now it's just a jumble of numbers. We need to find the pattern hidden inside. Now, we can't just count each number one by one. There are too many different ones. So the trick is to group them. And there's a simple 3-step process for this. First up, we decide how many groups or classes we want to make. Let's just say we pick 5. Next, we figure out how wide each group should be. Our data spans about 20 days, so making each group 5 days wide makes sense. And finally, we set the specific limits for each group. 10 to 14 days, 15 to 19 days, and so on. Okay, once we have our numbers all grouped up, we can create a really special kind of chart called a histogram. Now, it looks a lot like a bar chart, I know, but there's one really important difference you gotta notice. The bars are all touching each other, and that's on purpose. It's to show that the data is continuous, that an audit taking 14.5 days is right next to one that takes 15 days. There are no gaps in the numbers. And here it is, our histogram of the audit times. And look at that! A super clear picture just emerges from all that noise. You can immediately see a peak, right? The most common audit time is somewhere in that 15 to 19-day range. And you can also see that very few audits are super quick or take a really, really long time. This shape is telling us a story. So this is the really crucial point. We don't just make these charts to make our reports look pretty. The shape of the data is the reward. It contains so much valuable information. The whole game is about decoding what that shape is trying to tell us. Exactly. It's kind of like being a data detective. You're looking for clues in the overall pattern. Is it perfectly symmetrical? Is it all lopsided? Where's the big peak? These are the kinds of questions that lead you to some real insights.
For instance, data can be skewed. If you see a long tail stretching out to the right, we call that skewed right. A perfect example is housing prices, right? Most houses are kind of clustered around an average price, but then you have a few multi-million-dollar mansions that pull that tail way out to the right. A tail going to the left is skewed left. You see that a lot with something like exam scores, where most students do pretty well, but a few really low scores can pull the tail down to the left.
So we've added some seriously powerful tools to our kit now. We can organize data, we can visualize it, but I have to finish up with a bit of a warning. A cautionary tale, if you will, because sometimes the way we group our data can do more than just fail to tell the truth. Sometimes it can tell the exact opposite. Let's have a look at the records of two judges, Judge Luckett and Judge Kendall. This table shows the total number of their verdicts that were either upheld or reversed when they went to appeal. Now, obviously, a lower reversal rate is better. So, take a look. Who's the better judge? Judge Kendall has a 12% reversal rate. Judge Luckett has 14%. The choice seems pretty obvious, right? I mean, it seems clear-cut. Judge Kendall is better. But what if I told you there's a hidden piece of information here? What if by combining all their cases into one big table, we're actually hiding the truth? Are you still so sure about your conclusion? You see, this is a setup for a classic and kind of mind-bending statistical trap known as Simpson's paradox. It's this wild situation where a trend that you see in different groups of data completely flips on its head when you combine those groups together. Let's see it in action. So here's the twist. These two judges didn't work on the same types of cases. They worked in two totally different courts, common pleas and municipal. Now, when we break the data down and look at each court separately, the story completely reverses. In common pleas court, Judge Luckett actually has a better record. And in municipal court, well, what do you know? Judge Luckett also has a better record. Yeah, just let that sink in for a second. Judge Luckett has a better track record in both individual courts, yet she looked worse when we combined the data. How is that even possible? Well, it's because Judge Kendall handled most of her cases in the easier municipal court, where verdicts are just rarely overturned for any judge. That huge number of easy cases made her overall average look fantastic, and it completely hid the fact that Luckett was actually the more effective judge in every single setting. That is Simpson's paradox. It's a powerful lesson to always ask how your data is being grouped. So what's the big takeaway from all this? Well, we learned that we can take raw, chaotic data and actually find the patterns hiding inside. We use tools like frequency tables to just count and sort stuff, and we use charts like histograms to literally see the shape of our data. But maybe the most important lesson of all is that we have to be careful, because just lumping data together can sometimes hide the truth, or even create a total lie. And that really leaves us with one final question to think about. The next time you see a chart in a news article, or a statistic in a report, just ask yourself, how did they group this data? What details might I be missing? What hidden stories could be lurking just beneath the surface?